somebody comes by, I was like, put the camera down. Very nice. Look at those. I want that in my house. Those monitors up there. Is that the Miss for receptionist? What's that? Rosie? She said she had to be down with visualization lab until 2:30. She said that June E would be her escort at 2.
Awesome, okay.
We're still way early.
Yeah. He was the next person on the list to ask if he got recognized. And since you said Rosie, I'd be stopped there.
Yeah, so Rosie won't be here when we start, so she'll be here later.
Okay.
And June E
The
is.
June will start.
Yeah.
Okay.
So there'll be more of us, so we'll just kind of hang out until 2.
Yeah.
Like an RU kind of thing? Yeah, we could do that. We had an RU like a couple years ago, but we ended our first RU cycle, we didn't end up getting review because of working. But yeah, we're very interested in doing a community college outreach. We actually have one community college student that we're doing right now. It's kind of our pilot of how do we create an experience that allows community college person to attend school, work, and get everything they can out. We might be in there.
So I have noticed the incline, and before then it was very slow. And now that the higher, the better computers, Longstar, Mavic, you guys got the funds. I mean, they keep on pumping and getting connected with VOD and I mean, I could keep going, but you guys can go ahead. I'm open.
Well, I mean,
I'm here.
you're exactly right. The thing is, like, while a lot of research is done at Tacc, we're not necessarily it's not done just by Tacc. So we're a resource facility for any scientist that's got like a National Science Foundation project or other types of projects related to it. So corporate, sometimes we might see some crossover from DoD or Department of Energy. DARPA is asking us to help them put up a cyber infrastructure for research. What we end up doing is kind of like, it's like that middleware provider. Like, we have the resource, but we also, all of our research staff is kind of like the interface to everybody else. So you have scientists that want to do research, and this field is very, very new. Tacc is only 15 years old, and supercomputing has really blossomed in the last 15 years, which means that you have a lot of older generation scientists who are still in their career, but never did any of this stuff because the resources weren't available. So we have to not only provide them the resources, but provide them the training. Grad students do most of the work, but the PhDs are there to publish and put their name and present about the code that was written. So we end up providing the resources and then the training, as well as doing some research into new ways of using computing. So if there is a field, if there's a domain science field where the computing technology has not been developed for that application, then we do some of that research. We were recently, one of our neuroscientists was recently awarded a neuroscience award on how to use a supercomputer to do neuron mapping. Yeah, I don't even know what neuroscience is, to be completely honest. Like, that's in the brain. So yeah, we do some emerging technologies on how to apply computing in these fields, but a lot of the research that is being done and the discoveries that are being made are using our resources being done by other people that are funded by the National Science Foundation for doing research. So, like I said earlier, I'm one of a handful of people that has computer science, but we actually here have a lot of other fields of research, and we have one guy who's our leadership team member. He's the head of the data sciences group, or essentially the big data group, and he was an astronomer. He actually worked on the Hubble telescope, and he likes to say, I've never taken a computer science course in my entire life, and I have one book on computer science. And he uses all our computational resources, and yes, he knows computer science, he's brilliant, but he never came to us, he never started out being a computer scientist. So we're finding that, we're telling everybody, like, you don't need to necessarily be a computer science, but you need the ability to do some computer science in whatever field you choose to do, because that's the future of how things are done. Nobody wants to build rocket engines anymore and test fire them. We do it all in simulation.
Save millions.
Yeah.
Trillions.
Yeah. So you want to go see some stuff?
Let's do it. I'm
So
excited.
this is our
Thanks,
visualization lab. And have you talk to Andrew at the Viz Lab. Anyway, we do human interface experiments here. This is one of the visualization labs. Hey, Brian. Hi, I'm Torg from CQR Computer Science students.
Yeah, Brian, I can talk to you. Yeah, that sounds good. If that's okay with you?
Yeah, sure.
Okay.
I was really actually looking for Andrew. I just didn't want to hurt your feelings.
Oh, okay. Yeah, that's great. Yeah.
I just connected that guy in, so once it's done, just click enter and disconnect it and connect it to the batteries. And
Gotcha.
just that normal stuff. So, hey everyone.
How you doing?
Pretty good. How are y'all?
Good.
Pretty good. So my name's Andrew. I'm the. Oh yeah.
You guys are playing?
Yeah. Yeah. We're trying. We're trying on the other side. I'm the visualization lab manager here. I used to manage the lab on campus a lot, and then we had this new Viz Lab installed up here, and so now I manage this lab as well. And so Brian and I are sort of working to try and do experimental stuff up here. So did you take them down to the other lab by any chance? Okay, cool. So the other lab down south is actually like our production level lab. That's where we have like Stallion, one of our huge multi-tile display walls. So we have like a bunch of like head mount displays such as like the Oculus Rift, HTC Vive, Microsoft HoloLens. We have all those up here as well. But this lab is more of our like experimental system, sort of like where we can actually break things and try and create new products, new research things. So that's sort of like what we're working on right now. And so what we have here is actually a multi-configurable, a multi-tile display wall. It's called Rattler. And yeah, you guys just don't cross right here because he's doing a motion capture right now. Sorry. No, you're good. And so the way it works right now is that each column is 3 different computers stacked next to each other. So each monitor has their own native desktop machine to it. And we've made it so you can easily reconfigure them into like maybe a wall scheme. If maybe you want to give it more like a concave look, almost like an egg. Maybe you want just to have like a horizontal or a vertical rotation. So we made it so users can sort of move them around and put them wherever they'd like to test. And that's sort of like what we're also working with right now.
Sure.
We killed the server, so we have to reload. Yeah, so we have to reload this one.
Do you use VR with this?
What's
also?
up?
VR?
VR?
Yeah.
Yeah. So not specifically for this one right now. What we're actually trying to do with this one is do like motion capture. So that's what these 2 sensors represent over here. Is they're actually capturing that set of glasses right there with these 2 set of markers on them, so it can actually capture you in space. And so we're trying to do head tracking to sort of like calculate the correct viewing angles for the scene that we're loading right now in Unity. And so that is something we are working with. So almost like a VR without a headset for this guy. Yeah, and then on the other end, we also have the Oculus Rifts and the Microsoft HoloLens, as well as the HTC Vive over there. And so those are just normal desktop workstations. So any researcher who maybe wants to do any VR or just high computing work who doesn't necessarily need like a supercomputer, but can just use like a very high-end graphics card and CPU, can just come in here and do work on there.
So you said the baby's computer, right? Is it the baby's?
Yeah. These are like the small
least powerful of our systems.
Yeah, these are like the small ones compared to like the other ones. And so.
I'm pretty sure they're pretty strong, right?
Yeah. They have I think GTX 1070s in them. They have 1 terabyte of local storage. I think 256 gigabytes of SSD in them. So they're pretty powerful, even with like native desktops.
Correct.
So they're really nice. And so we use a lot of. Right now, we're using like Unity and also Unreal for some sort of general, VR stuff. But we've also used things. There's another group that's similar to my group called the SVT team, and so they use like ParaView, which is used for a lot of high performance computing. So if you want to do really, really large data visualization with supercomputers, that's what they use. So we're also seeing what things we can create with that as well. We also have like some mobile stuff also that we're sort of like working with, like with Vuforia and things like that.
So what's the divide between this Viz Lab and the Viz Lab that's down on the main campus?
So the Viz Lab down on main campus is more of sort of like a production level where researchers and professors down there can use those resources. And this is sort of like where we can try and create new resources and new things for them to use. But that's also a great space for people to maybe bring in for like education and outreach, because getting people up here can be kind of hard. And so down there, it's really great to maybe bring in like a set of kids who maybe aren't familiar with like high performance computing, even data visualization in a sense.
Okay.
It's a lot better for them for a student to go there instead of like having to come all the way up here.
Thanks.
Yeah.
Thank you.
Yeah.
Any other questions?
Oh, there you go.
Oh, there it is.
Hey.
Nice.
Crunch into the average.
Yeah, you're right. It worked.
So Unity, you mentioned that it does have clustered rendering already built into it, right?
No,
No?
that one is still special that you have to get. We do have right now it's in like their alpha stage, and we have a special license. You just have to contact them though.
Yeah.
I mean, you can actually just use the one we're using. It's actually, everyone has the same license.
So you're tying it into the perspective
Oculus?
protection.
Yeah,
right
yeah,
now, right?
exactly, yeah. And so we've done a lot of reworking of like sort of like their pipeline to make it more tailored for what we need.
Do you want to get a video of Brian kind of like playing around with the glasses
So-
and moving around?
I've got it right now. I don't know if I can like walk over there.
Yeah, just well, right here is probably good.
Yeah, I would say just as long as you don't run into the camera.
There's a bug, but I don't know if you can notice.
Yeah.
But that's all right. Everybody's zoomed into it. You see that? See how the red cube?
Yeah.
So I think what's going on is I think I know where it is. I think I forgot to divide by 2 on corner positions of the screens. That's fine.
Oh. And we're dividing by 1,000 by everything, right?
You're gonna be famous, Brian. Well, I mean, if you weren't already.
Yeah.
So you said this is like strictly to test viewing angles?
So this one is sort of creating a viewing frustum based off of like where you are. So it's constantly creating like the different angles based off of like where you're viewing it at.
And these are camera masks right there.
This is actually
Yeah.
okay.
Yeah,
You guys
so
are
the
working
idea
with-
here is we can.
This technology is not available
We're just
right
trying to
now,
do the
right?
test right now. such that
It is actually.
you
Sort
get
of,
the view
sort of,
the
but
same
this is like-
scene that you're looking
you guys
at
are
from the correct
making it better.
position.
It's nowhere near as
Some
mainstream.
windows and you're
Yeah,
flipping
like
through them at the
like
same
this, I mean, this is freely
But the
available.
goal here
That
is
is freely
we're using
available.
the
We're just
same
trying to integrate it in a
framework
very
that
like
people tend to
simple and
use
elegant way
for
that
the
people can come
HoloLens,
use
for the
it.
HTC Vive, for the Oculus Rift, and so forth. So if you develop content for the typical VR systems, we can then just take it and drop it in here and look at it. So whatever, a couple hundred megapixel.
Yeah.
This is like Minority Report kind of stuff right here.
Yeah.
Exactly.
Exactly. Well, that's what we're actually going for is
The holodeck.
So this is technically called the Human Data Interface Lab. So we don't like to think about human computer interfaces because computers are kind of, why do I want to still type into a terminal? I don't want to think about this as a computer anymore. I have this data, and I'd like to know something about that data. And so what I'd like is a more intuitive interface directly into that data rather than having to type every command that I want the computer to do.
Oof.
What are some of the models for that? So what would it be like for a human to interface directly with the data?
That's what we're researching.
Okay.
That's what we're looking into. I mean, one thing that our director of visualization is very interested in is what they call conversational analytics. So we'd like to get into, I talked to, computer, please bring up the telemetry reports on whatever, Star Trek. And so that's what she's very interested in. I think that's important. We're also interested in, so for example, here, one of the troubles is this is 9 different computers running the same game, right? And so one of the struggles you have is none of these computers have keyboards. None of these computers have mice, right? So if I want to interact with them, I need some way of interacting with them that they can all see and listen to and just respond when it's their job to respond. And so that's where the motion capture system comes in. So now I'm just in this volume and I can move around and they can all ask the motion capture system what just happened. And then we can update the scene. That's where we're at. This is research, so we're sort of at that stage of trying to work some of those questions out.
Yeah.
Yeah, and we also have like Luis he has his PhD in human-computer interaction, so he is the one that brings sort of like the UI and the user experience to the table.
And this is literally the first time that anyone has seen this working this well. So I would have a better answer for you maybe like next week. Now that I've actually been looking at my
I was pretty impressed when I saw you do that. I was like, oh, we got it working.
We got it working, yeah, exactly. And you all thought that I expected that to happen.
We came at the eureka moment, didn't we?
Yeah.
This is the applause moment.
Yeah, exactly.
Well, thank you very
Except
much.
not really, because there's still a bug in it, like I said.
Oh, but yeah, like I said,
But yeah.
it should be an easy.
Thanks for the time, I appreciate it. Thank you.
Stay right behind him.
Look at all that math on the wall.
Yeah, all your linear algebra is right there, or at least your 3D algebra. So it's funny that you should mention minority reporting. The main campus Viz Lab, they have a tiled display wall, and you'll see some photos of it later on, but it stretches from there to about there. It's 328 megapixel system, and it's extremely large, and they used to actually have a series of Xbox Connects up there so you could do skeletal recognition and like move all of the display things around.
That's cool.
But it turns out that you get really sweaty and tired after about 15 minutes of using it. So they got rid of them and just put in regular Xbox controllers.
Oh man.
Yeah.
I needed to lose weight.
I remember these, the old crate computers.
Yes.
Now your iPhone is faster than those things.
Yeah. So this is this is media from Cray. They were kind of like the name in high performance computing once upon a time. They're still mostly just a name that gets passed around by different companies whenever they acquire it. But they started the first parallelized systems for supercomputing. Essentially, you've got a whole bunch of different nodes that communicate with each other, divide up a task, do a large computation. Now, the reason why they are shaped in a C is because back then you didn't have fiber optics. You only had wire-based communication, which means if you have a long cable run, you have a lot of noise, it's not going to happen, right? So these are old vector-based systems that use specialized hardware that required each node to be physically close to each other. Thanks. And that's where supercomputing was. So this is a donation from the university system that was given to us almost 20 years ago when basically the chancellor of the university said, what do we need to be doing that we aren't doing right now? And somebody said supercomputing. And so this is the first system that Tacc had. And since then we've moved on to newer technologies, which I'll explain in a minute. Funny story about these little sofas right there. So a lot of people used to wonder what are those sofas actually for, right? We had a team from China come, and they were the Chinese supercomputing team that put up a system that was #1 in the world 3 years ago. And they talked about kind of the history of supercomputing in China and where their industry went. And they were told in 1983, in 1978, somebody gave them a picture of Cray and said, you need to build a supercomputer, this is what it looks like. And so they said, okay, and they had no idea what a supercomputer or how it worked on the inside, but they managed to figure it out, and they built their first system, and they had a picture of it from 1983, and it had sofas in front of it, and they're like, yeah, so somebody said it has to have sofas, because the Americans have sofas on their supercomputer, so yours have to have sofas too, so they put in sofas. It took them a while to finally get rid of the sofas. But.
Quick question on the, if you don't mind. This is an 83, the Cray?
This one's from the 90s. This one's from the 90s.
Okay.
They were built kind of like clustered like that.
If you compare to computers nowadays, what was because not a lot of information is online on those computers. What would be the comparison to computers nowadays? Could be like a laptop, could be the same power as that?
Power on a supercomputing system is difficult to measure for a lot of reasons. Like you might say, if you were, desktop software is designed to run in serial, right? You have one processor core running a series of instructions. You may be able to parallelize it. You may be able to have what are called vector operations if you're doing video games or the same operation on a bunch of data. So single stream software is not going to run faster serial software is not going to run faster on a supercomputer than it does on your desktop computer. Literally, they're the same hardware now. Like you can modern supercomputing started when people started going to Best Buy and just pulling stuff off the shelf and saying, I wonder if I can network this together. So it's really fundamentally the same technology, just, it may have more cores on board, or maybe clocked higher, you might have better GPUs on board. So if you took a system like this, you would say that yes, in terms of raw CPU power, in terms of the number of operations per second it can perform, obviously a laptop would be more raw operations per second. But you could also take the same type of operations that you're running on a desktop and parallelize it through a system like this, and you have different ways of measuring that performance. So you might get faster execution time for certain types of tasks than you would a modern desktop as a result of this sort of thing. So yeah, it's very difficult to compare these two. We like to say that yes, you do have more computational power in your phone, and if you were given a serial task, if you didn't write software, if you just wrote serial software, your phone might actually be a computer like this. But hey, Tim, it's not a one-to-one comparison.
Yeah. Just to visualize it for us regular users.
Yeah, it's kind of funny because so we have software systems that do this type of thing, and when you write scientific software, there are several different what we call message passing libraries to accomplish this computation, and some of them are like I pass data, and some of them are I pass tasks, or some of them are I pass a mixture of both of them, right? So we have one called OpenMP, and then we have one called MPI. I can't remember which one does which. And then we also have vectorization software. So stuff like related to GPUs or related to your processors that can do large vector operations at the same time.
Well, I don't like vectors.
Wait till I talk about machine learning. Your head's gonna explode. I read that chapter like 10 times. All right. So anyway, what I'm saying is that like it is somewhat difficult to conceptualize those types of things because I like to think of things as like there's one controller passing data between multiple nodes. Some architectures aren't like that. Some of them are kind of more like a community or just kind of a chaotic little anarchistic cluster that manages to like pull data from somewhere and it all just gets done at the same time. So I haven't had time to sit down and really explore MPI. This is Greg.
Remind me, I eggs.
Greg is in the life sciences department, which is why he has eggs.
No.
It's gonna go into the house.
So this is my computer science student groups.
Very cool. So I guess you guys started your tour then? What have you seen so far?
Yes.
Okay. Do you want me to tag along or?
Yeah, sure.
Do you want to?
Do you have a meeting or you?
Meeting's over, but can I drop this off at my office?
Yeah,
and
we'll
rejoin
kind of
you
take the
guys?
standard path. Yeah.
Okay, cool.
Yeah. So
Thanks,
let's
appreciate
start
it.
right here.
Thanks.
Thank you, sure. So fast forward to like early 2000s, Tacc was one of the first supercomputing research facilities to put together a cluster system because networking technology became fast enough once we had fiber optic technology to basically say now we can have what looks like your now standard blade-based servers, large racks of systems that are not shaped in like a C with sofas in front of them, but they look like if you watch that show Silicon Valley, they look like a data center, right? So this is a switch from one of our first large-scale systems called Ranger. And Ranger, each of these ports right here had 40 fiber optic connections. So you can essentially connect 40 individual nodes to one plug. So this thing is called a Magnum switch. They only ever made like 4 of these things. Now this one's sitting here just, weighing down the floor. Systems get retired as the technology gets faster, and the networking technology is faster. But kind of like the performance gap for a lot of supercomputing is based off of your network infrastructure between each of those nodes. So big leap in performance because of a big leap in networking speed. So speaking of things that are, ancient technology, your cell phone has more of it right now. Without reading the label, anybody want to guess how much much data this platter stores?
1,000 gigabytes.
That one right there?
Yes.
This is actually a plate?
You
This is a hard disk.
Good lord. From how long ago?
70s.
Okay.
Wow.
Oh, a few kilobyte.
Oh, okay, not that much.
This one is a 64 megabyte disk.
Oh my.
You could store maybe half of a digital album on this thing, or you could kill a human being with it if you dropped it.
Two, 3 songs?
Huh?
2 or 3 songs?
2, 3 high quality songs.
Oh my goodness.
Yeah. Data density has our ability to store it and transfer it has increased immensely. So we also have many different types of problems. We have problems of I need a lot of processing power, but then we also have problems of I need a lot of storage space, like archival, and then sometimes you might have the two of them, like I need to perform processing on a large amount of data. So the speed of how you read that data affects how fast you can complete that computation. So let's go look at some other stuff.
Good lord.
Yeah.
Imagine playing that in your car.
Let me grab this Nirvana
This is
song.
less convenient than an 8-track.
Let me grab my one Nirvana song. Hang on, guys.
So this is a lot of slides from some of the visualizations that our software visualization team has done. So instead of real-time visualization, let's say you've done a computation where you generate tons and tons of data, right? You might have some type of computer model that is maybe a petabyte of data. That data is not really useful to a human being, so we have to render it into something that a human being can see and interpret, and that's where software visualization comes in. A lot of this stuff was done using a software called ParaView, which is good at just taking numerical data and putting it into a 3D renderer. Cody. A 3D renderer or a movie of some type. So for example, this one is a simulation of ocean geothermal systems related to water. You can essentially simulate the terrain, geothermal sources, bacteria content, sun, El Nino and cycles, and it maps out essentially the eddies of the ocean. So you can imagine this whole entire thing as a current, but when you see the thing actually move, you'll see that all the currents have little eddies that look like donuts that spin through the water. And that helps you figure out where nutrient content is going to be distributed across the ocean or form, simulations for climate change, whatever you want to do with it. But all of this is essentially a render of the output of the computation system. So frequently what you'll do is you'll do the computation on one system, then move it off and somewhere else, do a render on it using a different hardware. So you can see that we simulate a lot of stuff here. We've got cloud formation. This is distribution of energy throughout a CPU. Over there we have propagation of water through a rock formation. This is turbulence inside of a supercell thunderstorm right here. And this one is early galaxy formation. Basically when you have nothing but clouds, what is it going to look like when the galaxy forms? And all of these are slides from movies. So if you look online and search hard enough, you'll find basically just films of all these things going. So the idea is that we've had all the math necessary to do these types of simulations for quite some time, but that math requires a ton of computing power. And now that we have that power, we can now do experiments that are too large in scale or too small in scale, or would take more time than you would have on the Earth, or things that are just far too dangerous. Do it all on a computer and just render the results. Then you don't have to actually do the experiment in real life. We've even done some services for Firefly space systems. They were kind of like private rocket systems, and they don't have the money to build a whole bunch of rocket engines and see what happens when they fire them up. So they use our systems, simulate it. There we go. Yeah.
So what's a typical runtime of some of the data crunching part, not the visualization part?
I think it depends on size and how much you're trying to grab as far as the amount of data you're operating on, how much dependency there is between different informations. So one of our big achievements is that we powered an experiment called the LIGO Observatory, the LIGO Gravitational Wave Observatories. So Einstein in the 1920s theorized that there is such a thing called gravitational waves, just like there are electromagnetic waves that do radio signals and light or whatever. There's essentially waves for gravity as well, right? But he theorized that because gravity is the weakest of all the physical forces, that it would be so small you would never be able to observe a gravitational wave. So sometime in the 90s, the NSF funded a $1 billion project over the course of 20 years to build essentially 2 observatories to detect gravitational waves. Like you're talking basically 2 super lasers pointed at like an angle. Like we built 4 Death Stars. Anyway, so yes, you shoot the lasers 4 kilometers this way. They hit like the best mirror that you've ever seen ever, and then they come back here, right? And the light waves interfere with each other, and then if a gravitational wave pushes through, it'll alter the wavelength of the light. Mm-hmm. But the distance that it alters it is only a 20th of a proton's distance, right? So because there's basically like, you basically like parking your car would probably shake it enough to do that. They had 2 observatories, one in Seattle, one in Louisiana, and they have to detect the signal at both, so the wave should propagate from here to there, right? Then the thing is, what does that wave look like? Because you're going to get some type of ripple pattern, and we have the math to be able to determine what is a possible wave pattern based off of simulating different types of events. So the next thing they had to do was generate 250,000 different possible events that would happen in space, like stars colliding, effectively, right? And then after that, they have to detect those events happening, but they have to do it fast enough to be able to say, "Oop, that's an event. We should actually record the data from here on out to get the entire wave pattern." Right? Now, when they started back in the 90s, we didn't have a lot of parallelized code. We had distributed systems for things that we didn't need in real time, but their code was very, very slow. So when they basically asked the National Science Foundation for another $50 million to build a supercomputer to process this faster, the National Science Foundation was like, "We gave you 4 super lasers, guys." All right. So they directed them towards us, and we helped them optimize their code to be much faster. We gave them 8x speed up on, I believe, even just the generation routine. It depends on which software package we're talking about, but we helped them optimize their code to run that system. Finally, when the gravitational wave event happened, when they turned on the observatory, 2 black holes collided 1.6 billion years ago. Eventually, basically during that month, the gravitational wave passed through, and we made that detection in 4 seconds by comparing the pattern to all 250,000 possible patterns.
Wow.
Yep.
1.6 billion years ago?
Yep.
That's insane.
Yep. Yeah. So, yep. You can, in other large tasks, Stampede, which they are replacing right now and cabling right now.
Oh, let me see that.
Yeah. We'll see that one in a second. Flash floods in Texas. You're right.
Just happened.
I know. Well, I was in Chicago, but I heard it was bad. Like, my house was just like a mess when I got back. But flash flooding, it's basically water coming down from the escarpment. You basically have a lot of rainfall in one place, and it just flows, right? Mm-hmm. And because it's water, you can simulate it very, very easily. And we also have sensor networks throughout basically all of our rivers and streams in Texas. They're run by Textile, where you can figure out in almost real time what the water level is. But you have to be able to predict where it's going to go so you can warn people to leave. Mm-hmm. Every storm is slightly different. There's a lot of erosion or whatever. So once upon a time, when they started saying, can we use a supercomputer to simulate it, they had really bad code and weak systems where you could take that data and predict and simulate it, and it would take 28 hours to figure out where it was going to flood. So flash would start, 28 hours later, you'd be like, hey, we were right about, where all the flooding went. So some researchers used Stampede to say, can we write better, faster code that's designed to run on a parallelized system? We would use this as a Tacc staff to make this run faster. That computation is now in 10 minutes, which is near real time. And it was persuasive enough to where the Department of Public Safety, is it DPS? Was it Textile or DPS? Right, it's on cell phone. What?
What was the question?
Who did the flash flood early warning system? Who has that system now?
Oh, I have no idea. That's.
He's recording video of that. It's going to be on YouTube.
That's not.
It's going to be a new meme. Greg's in there going, oh, I have no idea. Well, anyway, they built their own data center just to run that simulation as a result of the work that was done here. So those are the types of speedups that we're talking about. In fact, we have a group called HPC, Highly Parallelized Computing, or we sometimes say High Performance Computing. Those guys are, their job is to take your code and tell you how to make it run faster. And they compare their speed ups not in terms of time, but in terms of number of times faster. So the answer is very fast.
Every time.
Yeah.
So are those sensors, the water sensors, is there an open API that you can pull data off, that we can pull data off that?
Yes and no. So we recently worked with the Texas Water Development Board and some other aquifer management and well water management people. There are a number of different data sources. They have APIs. The quality of the data varies immensely and what goes into it. So for example, USGS has a front-facing map which you can look at. The API is not well documented, but it's there. So you can go to USGS and get essentially rainfall data if you needed to. Wells, Texas, I can't remember which commission it is. They keep well water data, but that well water data varies immensely in quality and time. So like, for example, we have monitor wells, which have data for every 15 minutes for 20 years. You might have one well that has like a scan of somebody's like notes from 1962 for the one measurement they took when they drilled a well, right? And that's just that. So we played around with that. We've helped some of the aquifer conservation districts say, how do we develop a system that integrates all this data together so that we can do things like simulation, so that you know when you have rainfall, how much is going into the aquifer, how much is runoff, and it's a matter of trying to collate all those different data sources together and make them talk to each other. So those are some of the types of problems that we work on.
I believe that when we're talking about the aquifers being affected, also our population has a lot to do with it. I think infrastructures. When we build more, as it's covered more land, less water is going into the ground. Is those kind of calculations are also added into your computations?
They can be. You don't necessarily require a supercomputer to do them. Also, simply because when you don't know much about an aquifer system other than being able to dip into the wells, right? The size of the computation doesn't necessarily warrant using a supercomputer. Now you do have to use different techniques to do it. So this is our shiny new computer, or no, not our newest one because Stampede 2 just is now being put in, as you can see. This one's called Hikari. High performance computing is extremely energy intensive. You consume a lot of power. In fact, when our data center is running at full capacity, when everybody's got got high system usage, it's effectively a 10 to 12 megawatt system, which means that at any given time, we're drawing enough current from the grid to power a small city. Right? Yeah. That's just during the day. At night, maybe there's less usage, although we try to run things continuously. People do scheduled jobs that run in the middle of the night. The entire data center is cooled by water, and so we have 1 million gallons of water out back that we chill at night to 40 degrees when it's colder and more efficient than pumping through our entire data center. Along in this process, you're basically saying you're drawing current from the grid, and then it's still very energy efficient because you get AC current from the grid, right? And then it essentially has to be turned into DC current. But we have a battery backup system which smooths out that current as well as provides a little bit of extra energy whenever it's like a brownout. So you go from AC down to DC, but then to get across the data center, you have to convert it back into AC, and then finally the system itself is going to convert it back into DC. Every single time you make that step, right, from AC to DC, then back to AC, then back to DC, you lose about 15% of the overall energy that you should be able to draw from it. So it's very, very inefficient. So this system, Hikari, is called a high voltage DC system. It does draw some of the current from the grid, but when you walked in earlier, as you guys passed that parking lot with like the covered thing, all that's solar panels. That is a huge solar array, and it's able to provide 350 volts, millivolts, I can't remember which, energy. And so effectively at any given time, you've got on a really sunny day, you can draw more than half the current directly from the sun in high voltage DC, right? And then the inside, on the inside, you guys familiar with liquid cooled systems? So this one uses cooling pipes, and instead of having to use pumps to pump and force the liquid through, the water is actually inside of tubes that are near vacuum, which means that as soon as it gets warm, it evaporates almost immediately, and the system just condenses itself, recondenses itself, and you can save power on even having to operate active cooling at that point. So it's a very energy efficient system. It was actually an experiment that was done by a company called NTT, and they more or less just gave us this system. So, hey Patrick, you want to talk about cybersecurity later?
Maybe.
Do you want to talk about it now?
Like what?
Well, this is Patrick. He is our security guy. They're all computer science students, and some of them are interested in learning about, security applications, kind of how do you get into it, what do you have to study.
Yeah. Well, I think if you're trying to get into it, you get a really good base knowledge of like how Linux works, how you would break it, and how you protect it from being broken. And then from there, you start working with systems that have been broken. Like I worked at a web hosting company, we had sites get hacked all the time, and you see different exploits and how they work. And if you run those exploits yourself, you can kind of figure out how to better protect against them.
Know thy
So that's
enemy.
kind of a good way. Say what?
Said know thy enemy.
Yeah, definitely. What we
Patrick,
do-
what was your background to get here? Where did you go to school? What did you
I
major
went to
in?
school at Oklahoma State University, and we had a information security option through the MIS program, which is Management Information Systems. So it's somewhat less technical than like a straight computer science, but my last 2 years were pretty focused on information security, so that was cool. We had like an information security club. There was a competition that all the colleges compete in called like ISAC, and I was part of that team for 3 years, and that was really cool. You build like your own little system with web, email, all these services, and there's like a red team that are attacking you. So you're 8 guys protecting against it. So, oh yeah, Texas A&M, they do it. Right? Well, so now I've been here, I do more like network security. So I work with a software called Grow a lot, and it watches all the packets that come through our pipes, and it puts them together. We have a whole bunch of bandwidth, so we need a cluster of servers that put these packets back together, and creates logs, and then you find interesting things in those logs and figure out what to do with them.
We actually hosted their convention. We hosted BroCon, right?
Yep.
That's a really unfortunate.
Patrick, do you have do you use like, this might be a silly question, but I'm gonna ask it anyway. Do you use like Norton?
Do we use what?
Norton antivirus?
A lot of those tools that you would see in the industry are all Windows specific. So for Linux things, it's kind of, there's two sides to it. Everything's free, but nothing's super well supported like Norton. Not that Norton's maybe the best option, but there are a ton of options in industry for Windows and Macs.
Typically, attack vectors in Unix-based systems are not based on viruses. They're based off of system exploits.
Yeah, we have over 10,000 accounts, and a lot of these researchers have accounts at other sites, and we may not be the best at security, but there's definitely other sites that get hacked a lot more often than us. And what happens when one server in a university somewhere else gets hacked is the attacker is able to move from their servers to all the other servers that those users had connected to in the past week. So these accounts get exploited, and then you'll see it come in from, you'll see a bunch of attacks over the next couple of weeks.
What's your protocol for this?
Well, we're part of Exceed. I don't know if you've talked about Exceed.
I have not looked at Exceed.
Okay. But it's a supercomputing club, like all the other big sites. All the other sites that are like us, who are funded by the NSF, and we talk and have security calls once a week. And as needed, if we have an account that's been exploited and it's an Exceed account, we know that account shared, then we'll all cut off access and force password resets.
I have a question. Are they normally looking for anything in particular, or are they just trying to mess with your system?
Well, a lot of them don't really know what they're doing.
They just want to hack it.
What's funny is we keystroke logs, so we can see a lot of stuff that they type. And if they hop into IRC, you can see what they're chatting about. And sometimes it's really interesting to see them be like, there's a command called ARP, and it shows all the computers on your local network. And a lot of times you type ARP because it's a good way to see what else is around me.
Yeah.
And they'll type it and then be like, there's 6,000 compute nodes in this network, and it's kind of funny.
So you said Grow is that open source security
Yeah.
for supercomputers or for all Linux types?
So it's been around in the supercomputing world and other like large institutions that have bandwidth requirements that exceed normal paid solutions. It's been around for 15 years at least. But nowadays it's been picked up by a lot of other companies. Amazon has a huge web instance. Like General Electric, they run it. So I mean, tons of other big names run it now too. But yeah, it's good incident response because it records like terabytes of actual network bandwidth into like single log entries. So you can keep row logs going back a long time and then look through and say you had an attacker come in, you didn't realize it for a couple days, but you want to see like any exploits that they could have downloaded from malicious sites, maybe in Russia. Like really easily you can grep through anybody that's downloaded something from Russia, and then you see like, oh, exploit.tar.gz, and then you know that's kind of what they use to exploit your system.
You got a good job, Patrick.
Yeah, interesting.
Well,
Thank
good to
you.
see
Thank you. Thank you, Patrick.
Step over here real quick. Power Graphs. You also see that we do have a user portal. It is very inconvenient to teach everybody how to run a whole bunch of Unix commands. Like I said, we have a lot of researchers. They really just want to get at their software without having to learn a whole new skill set. So one of our major products, it's hard to say it's a product, but one of our major things that we do is what's called cyber infrastructure. Cyber infrastructure is the idea that not only do you have the resources like our gigantic compute systems that do storage and processing and everything, you've also got the second layer of do you have all the software packages necessary to do engineering. We have a couple big packages that are standardized for many different fields of engineering. And then on top of that, how do you get your users to be able to use those systems? By integrating all the login stuff and access to those systems through various different types of layers that provide access through, we essentially create an ecosystem called cyber infrastructure, where at the end, the user should only see, I upload my data, I point and click and start a job for something very, very simple. I hit go. I don't have to worry about allocating the job or typing a bunch of Linux commands or transferring data back and forth. We handle all the software that does that for them. And at the very end, several hours later, after their job comes up and does their computation, they should get the result, possibly emailed to them. Right? So cyber infrastructure is kind of our main product, in addition to just the resources for computing. Any questions about this? Yeah.
You got a strobe light going on over there?
That looks like a wonky camera. Yep. I don't know what that is. It's half of it's out.
So I got a question about stampede. Isn't it supposed to be like twice as powerful as the current iteration?
It's 1.5 to 2 times. We haven't measured it yet.
Well, since it's like bigger and everything, is it going to draw more power? And are you guys like increasing the cooling capacity, or
No,
is
it's
the
not.
hardware just efficient?
It should not draw that much more power.
I think it's actually going to be smaller.
Yeah.
The dev count's going down.
Okay.
Yeah, we're getting more computation for less space.
Of course, that's
yeah.
technology.
Yeah. So they are running fiber optics, so that's hard. Don't be the way. But anyway, we have our Exceed systems. This one is not an Exceed system. It's called Lone Star 5, and it is a Texas University system partnership between A&M, Texas Tech, and us. So Lone Star 5, the sequel to Lone Star 4, is a Cray system. Now, when Cray gave us this machine, they basically took every single module that you would need in the operating system and loaded it into memory, which is very inefficient, right? So we basically said, okay, thanks, now we're going to put our own operating system on it. We installed CentOS and basically implemented a dynamic module loading system so that you're not using every single piece of software at the same time or every single capability, right? Lone Star 5 is not part of the Exceed network, but if you are at a Texas University system, if you're a student or a grad student or a professor, it's very easy to get access onto the system. In fact, we teach 3 classes in scientific computing that basically say, you've never programmed before, we're going to teach you C++, and then after that, we're going to show you some techniques for solving problems using linear algebra, and then how do I essentially use a linear algebra software package on a system like this to solve a problem in science and engineering. And so our students actually use this system, and there are a number of university professors that use this system to do their work. Yep. So we're going to come this way and see on these sides of the trash cans. We're just flattened against this wall and we'll try to top down.
All going
So right here, standing in front of you, is a system called Stockyard. And Stockyard is what we call our /work mount. It's a file system that's shared between many different systems. So traditionally, if you had an NSF system, you had your own computer and everything had to be done on that machine, which means it had to be versatile to do a lot of different things, which means it was good at nothing in particular, nothing specific, right? So let's say now in this new system where we have a data center or a whole network of different machines that you want to be able to use at the same for different purposes or different parts of your task, Stockyard is what gets your data from point A to point C. Let's say that you had your data that you were trying to process on Stampede and you did a simulation. All that would eventually be stored in Stockyard. Then if you wanted to render it in ParaView or do GPU calculations on it, you can move it, you can use Stockyard, read it from Stockyard on a system over there called Maverick, which is a GPU-based system. Ooh. Yeah. So it's kind of like our, you move stuff around kind of file system. We have 4 tiers of storage. Stockyard is going to be like the second fastest. We have one that requires backup. One over there called Corral, which actually is 30 petabytes, but it's mirrored in another data center in Dallas. And then if you want really long-term storage and you don't care about a backup, there's a tape system that's 160 petabytes that's in another building down over there. Yeah, it's so big you can't actually do a backup because the speed of reading tape is slow, the amount of data is fast. If we decided to ever back that up, it will literally take years to read all the data. Yeah. So our fastest system, though, is behind it. It's called Wrangler. Let's say that you have a data set that's like 4 terabytes, right? You need to be able to access that data extremely quickly for it to process in any reasonable amount of time. Yep. Wrangler is a Flash technology-based storage system, and it has different file systems on it, like Hadoop and other types of file systems, like a parallelized file system for, how do you best represent your data, right? And because it's Flash, it's extremely fast. In fact, single node, in other words, one node to one node, it can transfer 20 gigabytes in 1 second. Right. Yeah. So, you get an Xbox disc or a PS4 Blu-ray, you stick it in and install it, and it takes like 20 minutes. Yeah, that would take 2 seconds. Wow. And that's only single stream, and you can parallelize it, which means that if you needed to read multiple nodes at the same time, that's your speed up right there. But it's useful for data-intensive computing. So if you had extremely large data sets, you can do that. Like the entire history of the stock market. You want to do a simulation on that? Done, right? So that's what that system's for. Let's move this way. And you can see that we actually have a huge depth of systems, like more than 14 systems at this point. Down there's one called Chameleon.
Chameleon! I heard of that.
Yeah, I am on that project. I was just in that meeting before I came down here. So Chameleon is a test system. It's a test bed system. It's designed for effectively what we like to call computer science. A lot of what we do here is provide power for what we call domain science, chemistry, life sciences, physics, mathematics, right? Computer science is really how do we make all of that go faster, right? How do we make it go faster? How do we represent data? How do we represent communication? But there are newer fields of computer science. So when I took computer science in my undergraduate years in like the 90s, computer science, well, there wasn't really the internet yet, believe it or not. Right. So now cybersecurity is becoming part of computer science. Power consumption is becoming part of computer science. Being able to measure how much power your processor is consuming to perform certain operations. Representation, compression, storage, that's now part of computer science because we need to have higher data density. Algorithmic analysis, algorithms are very, very different than they used to be. Anybody do any sort of like algorithm analysis? Order of complexity, big O? No?
Yeah, next class, yeah.
Imagine you're trying to do essentially like operations on essentially, 1,000 elements, right? We used to say that when we did serial operations, basically it would take you 1,000 operations to do that, right? In modern systems, because we can vectorize any operation and perform one operation on multiple data at the same time, or even split it up and transfer it between systems, now computer science includes the field of if we perform vectorization or parallelization, how do we analyze that speed up when we're talking about, Big O is good for serial operations, but then it becomes really strange when you start saying, okay, that's great, you can do a sort, that would take n squared operations, but who cares if you have 6,000 nodes, right? So, let's go this way. And here she is. This is Stampede 2, the sequel to Stampede. Stampede is a very, very large, fast system. We measure speed in terms of, there are many ways of measuring speed, but the one that we use to measure this one is petaflops, how many quadrillion floating point operations per second, right? So in terms of petaflops, the original Stampede debuted at 6th fastest in the world when it was built about 5 years ago. 6 years ago now, I think.
It was like 2013, I want to say.
Really?
Yeah. It was like 2013 or 2014.
Wow. We got a really fast upgrade there.
I showed up here.
When was the big, were you part of the big Xeon Phi install?
No, I think that was the year before I showed up.
Okay. So it debuted at number 6 in the world, and it was an 8 petaflop system, 8 to 10 petaflops. And a lot of the power is derived from the fact that we have a lot of cores inside of this thing. 6,000 nodes with over 520,000 processor cores. And to get the number of cores that we needed back then, we used a technology called MIC, Many Integrated Cores. And it's called a Xeon Phi coprocessor. It's a big, gigantic silicon brick encased inside of aluminum, about this big, that attaches into a specialized bus. Right? It's big.
It looked like a video card. Yeah.
It looked like a video card. It weighed like a brick. Right? You don't want to drop it on anybody's foot. And so, at the time at which we installed Stampede, 2 things had to happen. First of all, we had to get rid of previous systems, including Ranger. Does everybody see that metal border right there? That was the original data center. And as soon as we got the grant, we said, hey, university, we got a new supercomputer. We need more building. And so they built this entire section of the building very, very quickly. And then it housed Stampede. Stampede got in, and at the time, the mics had just hit the market, and they literally were not available physically in the US at the time the Stampede was installed. So Dell put in all the racks, but then a boat arrived from Malaysia with all 6,000 of those mics, and they had to pull out every single node and unscrew them all and jam them all in. And that was an all hands on deck. All hands on deck. Our admin staff, one of our people who does essentially human resources for us, she installed more than 100 of them herself. Wow. Yeah. So now, we're 6 years later. We actually did an unsolicited proposal for this. So typically, NSF says, all right, we want a supercomputer built, submit a proposal that says you're the most capable institution of housing a supercomputer, right? And that's how we got the grant for Stampede 1. At the point at which we proposed for Stampede 2, there was no open solicitation. We basically looked at them and said, Stampede 1 has had so many millions of hours of compute time, and it's at, always at least 95% capacity, and there's always a job list twice as long as there is capacity for Stampede 2, Stampede 1. You need a Stampede 2. And so they basically, the NSF said, yes, we will buy you a Stampede 2, and now we have a big upgrade. So they're replacing all of the technology with new processors that actually have most of those cores that you get on a mic integrated onto a single CPU. I'd take you in, but we are actually operating on the data center now, so we can't really go inside of there.
When they opened the doors, it was very loud inside. Is it always like that?
Actually, it's quieter now because they're installing the racks. So some of the racks are down. But so what you don't see right now is that essentially we have outward-facing racks, and then we have the fans, the active fans, the in-row coolers, pulling in cold air and then pulling them out, right? So we have essentially the outside is cold, the inside is hot. We have sealed doors which separate our hot rows from our cold rows, and so there's a huge temperature differential from running the CPUs. So it'll be about 6, 7, 8 degrees hotter inside of the hot rows than it is on the outside. Although I've been in there on some days when it's we're at literally 100% utilization, where the temperature differential is very little because we're consuming cold air so quickly in that side of the system. Lone Star is actually liquid cooled on the inside. There's pipes coming up from from the subfloor into the system to cool it off. That subfloor right there, those panels, there's about 3 more feet down before you hit like the foundation. There's pipe running through there. We put little orange cones up whenever we pull up the panels. I tell small children not to fall in. So lots of power.
This is gonna be out finished this year, right? Later this year.
We hope so. It should be done within a couple months. Like we should. So there's a prize called the Gordon Bell Computing Prize. Gordon Bell is basically a competition which says, what is some type of new computation that you run which is scientifically significant that required like a lot of speed, some really good code to run, right? So Stampede 1 and systems like Stampede are in high demand for Gordon Bell runs, simply because systems like this are very rarely accessible to the public. So although currently it is the 12th fastest system in the world, it is the only one in that top 500 list at the top that's publicly accessible to scientists, which means that the systems that are faster are, basically, they're either in China, China does have a large number of supercomputing systems, or they might be systems that are Department of Energy, Department of Defense, and you can't access them, or, that shady one with the NSA that they do whatever it is to do with it. We have no idea. But this is the one that's publicly accessible, so it's in high demand for Gordon Bell runs. Our goal is to get Stampede 2 up in time to do Gordon Bell submissions, so that at Supercomputing 2017, which is our big supercomputing industry conference, whoever gets that prize, we're hoping we'll have run it on Stampede 2.
Now, as you construct it, are you rolling it out per node that's finished, or all at once when it's all done?
Racks, like rows.
Okay.
Yeah, and it's essentially a tree. That's how the network is arranged, a fat spanning tree. So they're essentially doing it by network because we still have to run jobs on it. We're also having to transition our users over to the new architecture, which means to capture that speed, they have to rewrite some code to take advantage of it. We do have some other interesting systems, like, for example, there's one back there called Catapult. It's a different architecture. Instead of traditional processors, numeric processors of numeric instructions, it's called FPGA, Field Programmable Gate Array. And the idea behind that is that the entire CPU is a bunch of like tiny microgates or microcores or clusters of informations. And then instead of writing a program, like if you were writing an assembly program, you'd write in the opcodes and what data and what registers to move around. You actually write a system descriptor language which rewires the inside of the CPU to perform that specific calculation, and then you just stream calculations through in parallel.
So we actually just got a big grant called NeuroNext from one of my colleagues that we're going to be, I haven't even read through his proposal, but I know that in the past that he's worked with essentially taking, like whenever you go for an MRI or something, they take like scans of you, and so they've worked with our biz folks in the past of how can we turn this into like a 3D model that someone can sort of interact with, can we get it a little bit more user-friendly where it looks like movies and you can sort of, move the slider and slice through the person, things like that. I mean, how can we better enable doctors to make decisions based on the data that's available? So that's really big as well. So yeah, that covers, most of it.
Well, I believe that at one time you never thought you were going to be in this kind of environment, but since you've been here, has your perception of what they're doing here will have a greater impact on society?
I would definitely agree with that. It's hard to really, yes, no matter what, my impact is greater just because I actually have the chance to touch more, not really touch, but just touch the research with more people. So like I personally provide support to researchers around the world. So I am helping them improve their research methods on a daily basis. And so it is not necessarily my personal work, but I am making a great impact, I would say.
Facilitating.
Yes, exactly.
Panels, whether
I mean, so people here, so like, I guess HPC is a great example. Life sciences is similar to them, where some of them have direct research. So I'm on 2 research projects that are essentially my own. But we also, people come to our systems, they don't really know the best way to use them, or they come with code. It's kind of like the gravitational wave project, where it was just slow, and we will help them improve their process. So yeah, it's a lot of people here are just helping you speed things up. So what are the best ways?
With this computer, it's good. No,
And there's always, we've got a computer for every problem essentially. So I guess you guys will be covering Big O soon. So I don't know, data structures will be eventually, I'm guessing, if you haven't already started that. And so starting computer science, it was hard to, I don't know, we learned all these data structures, we learned all these algorithms, and it was before I hit really domain science, where you hit the data sets that would essentially grind your algorithm to a halt if it were improper. If your data structure is meant to, I guess if you need to do updates on the data structure and it needs to rebalance the whole tree or something, if you do that in an inefficient manner or at the wrong time, that'll just really break everything. And so it's, once you really hit a huge data set, that these things will start to really this is cool now. I see why I'm spending all the time learning about this. What else? Domain science, life sciences is kind of, most science you can apply to pretty much any field, but life sciences is one of those ones that's kind of, I don't know, maybe I just see enough pieces that I think I can apply life sciences to anything. Even with when we were talking about the aquifers, sort of thinking about you drill down and you try to figure out what's the probability these wells are connected. There was a cool research project where people, so not quite water, we're dealing with, in this research project, they were questioning oil now, where if they drilled down, what is the probability that these 2 oil wells are actually the same oil well? And so instead of spending a ton of research money trying to figure out new radar techniques to actually see underground, they actually sequenced bacteria that were living in those wells. And so they could essentially, if you've ever heard of 23andMe, where they essentially map out your ancestry, they can do that with bacteria as well. And so if they see some sort of unique mutation that's shared between the 2 populations, they say, oh, these have bred together, and so they're interacting. So we know that there is some pathway between these 2 wells, which is, it's high tech, but it's sort of thinking out of the box of how can we think about this problem. So.
Can you talk through your educational pedigree and what your interests were and how you ended up here?
Sure. So high school, I really liked math. I did not. So high school was, I graduated in 2006, so that was 2002. My computer science course in high school was programming basic on Apple IIs. So we did not really have a computer science budget. But I was always a computer nerd. And so even if it meant programming on my TI-83, that's what I was doing. I knew that I liked computers. This was my hobby. This is where I spent all my time. So I went to school for undergrad in math and computer science. Just based on my experience in high school, I didn't really like the way that biology was taught. It was mostly memorization. It wasn't a lot of, I don't know, I really liked the experiments and actually learning how things worked. I'm not sure if that's more of the engineer in me or the scientist, but I loved that experience more. And so it was finally my last year of undergrad where I had a math project and we were simulating it in a coli cell and exposing it to different environments to see if it would grow or die. And so that was cool. So that was just a big model simulation. And And so that's really where I got involved in bioinformatics. And then from there, it was just grad school for bioinformatics. I mean, yeah, I had no idea I was going to end up in anything biology related. But
Your undergraduate degree was computer science?
yeah, computer science and math.
So based on what you know here, what you've seen here at Tacc and sort of the capabilities here, what are some projects that you would recommend for freshmen, sophomore, juniors? Because it's still very much what I would consider to be old CS in most universities, not what I consider new CS. And then when students get out, there's sort of a latent retraining period or reawakening period.
Yeah.
I think we're missing something.
There's so many, there's so many, with the whole hacker maker movement now, there are so many projects out there that touch the realm of computer science and domain science, which is what I am usually exposed to here. There's always a new way to apply computing to solve a problem or figure something out. I'm not even, I mean, it could be anything from data analysis of, I don't know, you could measure data around school and analyze it. I mean, you could even have, I don't know, I mean, Twitter firehose, something that's just too complicated to actually figure out by hand, or that's just too much of a mess to like see the trends with the naked eye that you need a computer to figure out. I'm not quite sure. Life sciences a little bit more. It requires a little bit more background knowledge in just the data formats. It's not. I mean, it's completely accessible. Usually, all the data that is produced, like right now, if you're funded by NSF, if you produce data in a lab, you have to publish that data for everyone to access. So it's all out there, as long as it's not human data. Just because you don't. Right now, it's privacy concerns. Everything from insurance companies being able to predict what diseases you're going to have later in life to you just don't want people to know that you are susceptible to a certain disease. Yeah, so plant data, bacteria data, pretty much any insect data, animal data, that's out there. You can, what is it? I did like a little tiny demo where you essentially compare genomes. So if you get into like, what is it? Essentially string comparisons. So, I mean, all the genes, so you can look at assembled genomes. It's just a long string. You can use different string comparison metrics and compare those genomes, and you can construct a phylogeny, essentially like a tree of life, like a small one, and compare it to the real thing, seeing how good just a numerical analysis does, based on compared to a biologist that spent their whole life studying this organism, and they say, oh, this one is a descendant of this one. Things like that. I guess, that's a hard question, I guess.
How about like, have you seen the Rosalind site, the problems
Yes.
of Rosalind? Is that useful to dig into?
That's real. All the Rosalind stuff is real. I highly recommend it.
Okay.
Yeah, so I actually did an undergrad, when I was in grad school, or when I am in grad school, I was part of a bioinformatics for undergrads club, and so that's essentially one of the things that we used to, I guess, I don't know, we had a club, a club tag, and so it was like how many people can we get to a certain level on that site. So yeah, but all those problems are real world.
Okay.
Trying to think what else. I don't know. Off the top of my head.
So what about a project to get a bunch of Raspberry Pis and try to build a cluster? Is that useful?
That's real. We did that.
I have a solar power one sitting on my desk.
Okay.
Using some zeros, yeah.
Yeah, we had our first Code at Tacc summer camp that we do for high schoolers. We actually networked them all together, and we ran a real HPC benchmark on it, and we got number 2 on the benchmark, so we were in the top 5 or number 2 on it. And I am very upset with number 1 because I'm fairly certain that they lied about their power usage. Because it was something, because it was like an NVIDIA GPU that, and an there was no way that it was, I think they quoted like 50 watts or something.
50 watts?
Yeah, it was,
For the entire system?
yeah, and I looked up the metrics on the GPU, and it's like the average power usage is like 150. I'm like, that's, no, someone needs to check this.
It's like 20 watts idle.
So was the cluster that you built out of GPUs, or was it out of Raspberry Pi?
Yeah, it was just Pi's. We had and we had these students network them all together. So it was a giant like mess of cables in the end. It was great.
How many did you have? How many Pis did you have? I'm asking because I'm looking for high school projects.
Yeah, we had 32. I mean, so if you want high school projects, you can, so Slurm is our scheduler. So that essentially, if you've heard of like stuff like Docker, it's essentially like a load balancer. So right now, whenever you say, I want on the cluster, I need to do this much work and I need this many computers. Slurm is what we use to manage essentially that, I guess, that environment where you say, I need this many computers, and Slurm says, okay, I have this many free right now, or you're gonna have to wait this long for these to free up. And then it will essentially provision those computers, like it cleans up the environment. So nothing is left behind by the previous user, and then you're essentially just given free reign on them. Everything except root access. So you can spin up that software. You can learn how to provision like a real cluster like that. If you want to get crazy, you can learn about distributed computing with MPI. Raspberry Pis now, they're all multi-core, so you can do OpenMP or something called Silk, which is a little bit, it's nicer. If you're, I don't know, it's a little bit more like worker paradigm, but everything is multi-core now. So one of the projects that I'm doing right now is trying to figure out what bioinformatics code will actually work on our next generation of Stampede. So right now we're coming from around like 3 gigahertz on our old Xeon processors, which are more like a desktop processor where it's, we have 16 to 32 cores, which is a lot, but they're using a lot of power, and they're pretty expensive at that point when you've got multiple sockets per motherboard. To the 68 core Knights Landing, and those are running at around 1.2 gigahertz, so it's like a little bit under half the speed, and you have to have code that is not serial pretty much at all to actually get speed up, or to even just run at comparable speed on the normal Xeons. So, always things to think about. It's always, we make it complicated because so we're essentially provisioning an environment that people are going to use thousands of times. So we set it up once right, just to make sure that everyone has a good experience. So.
How many people here have experience with Linux systems? I guess like I would say that being completely upfront about kind of like the learning curve to be a functional person here at Tacc. I did my computer science degree ages ago. I wasn't that proficient at Unix. Eventually I started teaching networking, and we all had Unix-based networks. And the learning curve on back then, where you basically had to install a whole operating system, you couldn't virtualize it. It was very, very difficult to get your teeth cut on Linux, just because very, very high learning curve for very little payoff, right? But now with the maker culture, especially with Raspberry Pi, what we found with it is that like you can take a kid and get their hands dirty on Linux, and they've never touched any of that ever before, and it's easy to get into working in the command line at that point once they get comfortable with it. It's easy to do programming, especially like physical programming in a Unix-based environment, and so it's personally for me, like becoming more familiar with Linux was a matter of just getting a Raspberry Pi and learning to configure it to do the things that I wanted to do. So like if you've ever wanted to set up like a DVR system or some a home theater PC or whatever, instead of devoting a whole Windows box to it, now you can do it on a Raspberry Pi, but you you get your hands dirty at first. It's like learning how to cook, you know? Follow the recipe. Don't deviate from the recipe, and eventually figure out what all those pieces in the recipe mean. And then you're like, oh, now I know how the system works, and then you can improvise a little more. As far as like setting up a cluster, that was even just getting two little Raspberry Pis and getting them to run together as a cluster was a high learning curve at first, but now it's like, oh, these are all fundamental skills. So one of our projects, like when we built Hikari, was like, hey, what if we had like a little teeny tiny Raspberry Pi based Hikari that you can essentially power with like a 12-volt solar panel, and or a 1 amp solar panel. So we got that working, and just even having just two $5 Raspberry Pis that you have to learn to install Linux on first. Second thing is you have to configure it so that it does have a network. You have to configure its host file so that they can see each other. Then you have to exchange keys. Then you have to install the networking library, and that requires a little bit of how do I compile something? If I need to recompile it, how do I download software using Git so that I can just, and run all these different C++ tools. All those little steps just for getting these two little computers to run one benchmark. Not very well at all. You learn a lot, and it's a useful skill. But the entry is not costly anymore, and it's not as difficult as it used to be. I would say that is a fundamental job skill, is understanding a Unix-based environment.
Mr. Walsh, when you something like that.
I'm on them.
Well, I'm glad that you have a professor that's willing to let you explore this. When I was a computer science student at UT, it was just expected that you would learn this on your own, and it's still kind of that way in the computer science department. The learning curve at major university computer science departments is extremely high. It's not geared for people who are just beginning to learn computer science. That's the unfortunate part about it, is that if you're entering into a CS department at a major university at UT, it's expected that you've already taken at least an AP computer science course at the high school level, and that's what the entry-level professors teach towards. And there are fundamental skills like how do I operate in a Unix-based environment or set that up. They don't teach that as a course. They expect you to kind of go out and learn that on your own, or get an internship where you would get that experience on your own. So if you get the opportunity to have some guided instruction on it, that's a really big deal.
I did that over Christmas break. I got a Raspberry Pi and set it up as a home NAS.
Yeah.
It took 3 weeks to get it working because all the tutorials
How
were
many times
based.
did you start over? Because that's.
I want to say, I don't remember exactly, but it took me 3 weeks to get it starting because all of the tutorials were based off the older operating systems that were like 2.5 years old. So I had to go through and mess with everything.
Yeah.
But I got it to work.
Yeah.
That sounds like a lot of fun.
That was not what I would call it at the time, but yeah.
It takes a certain kind of mindset to like think it's fun. Like some people like woodworking. They think that's fun. Not so much. I'll build something if I have to, but I don't like to sit there. But that's kind of like a thing that you can get involved with. Out of curiosity, for you guys that want to do mobile and app development, have you gotten your hands dirty with that yet?
Not yet. My experience has only been with C++ coding.
Yeah. The learning curve on app development is actually, it can be pretty high. I taught Java for a long time, and eventually I switched over to teaching Java and Android development. I don't want to go on record as saying that I hate Java, but I hate Java. It's nothing like learning, as if Java was already complex enough and kind of a clunky language for certain things. Now you not only have to learn the language, but you have to learn how the system works. And that's kind of where, when you're talking about app development in any environment, unfortunately, it's not just the language that you're learning, but how everything is put together. Like on a mobile device, you have something called a UI thread, and you don't want to run like your network operation on a UI thread, or you might have something where you send it off and you're going to get a callback, and it's strange and very, it feels very, very specific, like it's not transferable. But if you do enough of it, you're going to get used to the discomfort of it and eventually understand that all these systems share things that are in common with each other, and you begin to learn the commonalities between them. They are all based off each other. Recently, I was finally forced to learn how to do an Angular app. Are you guys familiar with Angular? Angular is a framework for web development for essentially microsites, or it's not really microservice, but a microsite that uses what's called the model view controller framework. Most like Django on a Linux system, and then Python, and something sitting on top of it before you get to your web page. This kind of crunches it all into one JavaScript library, and then they decided that JavaScript wasn't good enough, so they made another language called TypeScript, which is a language that generates JavaScript so that you can have your web page. And yeah, we had a couple leftover projects from a software engineer that were in Angular, and I talked to one of our software engineer people saying, hey, do you know anything about Angular? And all I got was cursing for half an hour. I hate Angular, what is this stupid, and every single time you pick up a new system like that, it's going to be extremely uncomfortable. I think it took me like about 2 days of just repeating like the same, like almost a hello world level project before like, oh, I understand how this works now. I'm beginning to like move past it. But in this industry, if you go into software, you will forever be retraining yourself. And I would say that the only thing you ever get used to is the discomfort, but you get better at it.
New languages.
New languages, new frameworks. There's always something new to learn. It's a rapidly developing field.
So what language do you guys use for most of the computing that you guys do here? Is it just C++? Is that the prominent?
And Fortran.
Great.
Not even kidding. So Fortran is like, did you guys see Hidden Figures?
Yes.
That they were using Fortran, right? That was Fortran 1, and that was a very old language. It was very strange. Like comments begin with the letter C for some strange reason. Like so don't name them anything a letter C unless you really mean it. And that code is still around. So you have a lot of scientific code that's still written in older Fortran, and they revise languages very quickly now. So it went Fortran 1, 2, 3, 4, and then like Fortran 72 or 76 is when it changed dramatically. But it's still technically supposed to be backwards compatible. So we're now in the 2000s. We have modern Fortran, but every Fortran thing is still almost backwards compatible all the way to the beginning. And people don't rewrite that code; they just reuse it. So like we have another lab here at Pickle called Applied Research Laboratories. They do mostly Defense Department work, so I don't really know what they do there. Top secret. They really can't talk about it. Like they have to go when they program in clean rooms. You can't take a cell phone into that room.
Oh, wow.
I'm like, so how do you look anything up on Stack Overflow? And they're like,
It's like a skid.
You have to.
what's that?
Like a skid.
What do you mean?
It's
High
like a
security
sensitive,
area.
compartmentalized information space. It's things. You say they're not allowed to talk about it. They can't take in media devices. Nothing recordable.
Yep.
You can't write anything down.
You have to check in, check out, just to go through the doors.
I wouldn't be surprised if they programmed like buck naked. But
They all do have a solid romance, right?
individual, it's all individual, it's private, no windows. Well, anyway, so one of the guys said that like he was given a piece of Defense Department code that was written in Fortran 4. And he said it was almost unreadable, but it still has to integrate into a modern system. So there is a lot of legacy code for things, and Fortran is something that's hung around for a while. I recently read an article that apparently COBOL programming language is still running on more than 80% of financial systems, banks and ATMs. And now you can get a very good job if you know COBOL, because nobody knows it anymore. It still has to be maintained.
Who's teaching the COBOL class now?
A lot of money, a lot of money.
There's a YouTube tutorial somewhere.
Why don't they ever update those codes? Why do they insist on continuing to use them instead of just?
Fault tolerance. I mean, when you think about like a system that is designed, that has to have almost no failure. It has to be a system that has experienced everything and been around for a long time. So for example, there are Defense Department systems that still use 3.5-inch floppy disks because they're very, very stable. Like everything that could have happened over the past 20 years has already happened to it. Microprocessors, like for example, the space shuttle, you know, when it was retired, it was still using like a 286 computer on board. You guys don't know what a 286, do you?
We'll look it up in the museum.
An old computer.
They're very, very, very old. Like the 286 computer, that era of computing was like before color graphics and no hard drives. You had 2 floppy disks and an IBM system that had a 286 processor inside of it. eventually it was 8086, then became 286, 386, 486 Pentium, and that was like in the 90s, then Pentium 2, 3, 4. Eventually now you're under Xeon or Core i5 series or whatever. So you're talking essentially, if we're in our 12th, 13th generation Intel processors, this was effectively a second generation processor. But they still use all of these old systems because they're very reliable. They've been through all the certification processes. They will not fail, and so there's no point in replacing it if it works, because if you replace it, that means that you have to go through an entire process of making sure that a system that cannot fail, otherwise bad things will happen.
Correct. It's not broken.
Yes, if it's not broke, don't touch it because it might break.